Hi, my name is Dr. Jay and I welcome you all to this sixth video on GATE series for metallurgical engineering. In this video, I will be talking about line defects or dislocations. So, line defects or dislocations are linear or one-dimensional defect. And since they are defects, the atoms which are surrounding it are misaligned. But the atoms or the defective points, the position or the locus will be such that they will lie along the same line. And that is why they are called as line defects. Now, what causes line defects or dislocations in a material? So, dislocations can be formed because of two reasons. First is if we apply stress more than yield stress, which is the point in the stress strain curve where stress is no longer proportional to strain and the material will start to deform plastically. Or the another reason of formation of dislocation is it may occur during solidification. Now, are dislocations useful? So yes, dislocations are very useful when we want to explain the deformation and strengthening mechanisms in metallic materials. Essentially, in deformation, we talk about movement of dislocations or slip. And strengthening, we are talking about restricting the movement of dislocation. So if the dislocations are moving, deformation will occur. If the dislocations are not moving, strengthening will occur. So if by some means we can stop or restrict the movement of dislocations, we can get strengthening. And if we can allow or if we can help in the movement of dislocation, then we are promoting the deformation mechanisms. But these dislocations are not seen in ceramics and other materials because it is very hard for them to be created in ceramics and other materials. Now, there are three types of dislocations: edge dislocations, screw dislocations, and mixed dislocations. Mixed dislocations is nothing but a combination or a mixture of edge and screw dislocations. Now, let's talk about edge dislocation. Edge dislocation, here what happens is the type of line defect in crystal lattices in which defect occurs either due to presence of an extra plane of atoms or absence of half a plane of atoms. So if we have extra plane of atoms present or if there is an absence of plane of atoms, then we say that it is an edge dislocation. Here what will happen is, if you see the above scenario, the atoms above the dislocation line are squeezed together and atoms below the dislocation line are pulled apart. Now, there can be different ways by which we can represent an edge dislocation. This symbol represents that extra plane of atoms lie above the dislocation line, and this symbol denotes that extra plane of atoms lie below the dislocation line. So this is about edge dislocations. If there is a presence of extra plane of atoms or if there is an absence of half a plane of atoms, then we say that this dislocation is edge dislocation. Now screw dislocation. In screw dislocation, it looks something like this. Here, the planes of atoms in a crystal lattice trace a helical path around the dislocation line. So suppose you have a dislocation line, then there will be a helical path which will be created by the plane of atoms around the dislocation line. And the upper front region of the crystal is shifted one atomic distance to the right relative to the bottom portion. So here it is twisted. The screw dislocation will be moving like this. In the edge dislocation, it was relatively easier. In screw dislocation, it is relatively hard to find because here the movement of atoms is slightly complicated. And this is how we represent a screw dislocation. And these are two examples by which we can see whether the material has edge dislocation or it has screw dislocation in it. In the next video, I will be talking about slip and slip systems. And if you like my videos and if you want to watch more videos and if you want to support my work, please subscribe to my channel. Thank you.